if we just take it with respect to y. And now if you do the same thing for x, you also hopefully that makes sense. The basic integral formula is x to the m dx, right? Where it's just x to the m plus 1 over m plus 1. Moving on. The next one that I feel is important is the ln of x, or the natural log of x. So you just get 1 over x itself. So that's basically what you're doing here. So here, but in this case, you're using also the chain rule. It's mixed together. So moving on. 9. Same kind of deal with here, but this one's kind of non-intuitive. I wanted to go over this because it is non-intuitive. Basically, what you're using, not sure, but basically that's what you're doing. Anyway, let's move on. And then all the other integrals, make sure that you just look up the page. So I'm using, on this one, I'm using which page, because that might be important if you're trying to look through the manual and you're just y and x. And that's not a problem. But anyway, let's move on. Let's continue. So now I kind of wanted to go over this concept of a Taylor series. You may run into this on the FE. For example, let's say if you have a function of x where it's sine of x, sine squared of x, and you want to basically just get a fourth term approximation, right? And so if you want to get a fourth term approximation, what you would basically notice first is that you just kind of go through the formula as well as you possibly can. First, you would say, okay, let's get series is you're taking a function. Let's just try to let's see what sine squared is about. You're taking a function at any value a. What you're doing is you're at any value a, you're trying to figure out a approximation for the value of basically for what the function should be around that. So because you're essentially using an approximation that's surrounding it. So a typical series is trying to sum every element up to where you get exactly sine of that. So, but you need a point because it's going to depend upon, it's going to be contingent upon how it's going to look. For example, you might have a cubic that is going to be like that, approximately like that, or maybe something else that might even be a line where you just simply have a line that looks like that. And so you're doing it around A, and so then that's why you need A. So because you need a point of reference, pretty much. So it doesn't really matter what it is, what the point of reference is for our purposes. So we're just going to say A. A equals 0. So if we start off with A equals 0, then the f of A is 0 because sine of 0 is 0. Then now let's try let's try this one. So let's focus on this one now. That's going to be f prime of A is going to be, you have f prime is going to be 2 sine of x cosine x, right? And that has to do with remember the identity double angle formula. So that's a sine, which means at A equals 0, you get 0 f prime of A, right? So that's essentially 0. And then now this term, let's see, now we take the double derivative and we get 2 cosine of x squared, but then you have a sine, so you then have a sine because well, it's going to be minus sine squared of x, because you're basically doing the product rule here. So you have the cosine, the derivative of the cosine, and then the derivative of the sine, separately. So in this case, you then have at A equals 0, at a equals 0, then you get f prime equals basically just 2. So, yeah, so then that would be, but then you have a 2 factorial, so then this ends up just being x minus 0 squared. So then now if we try to take the triple derivative, we get 2 times basically what we had earlier for sine, but then now we have, cosine. We have minus sine of cosine of x, and then in this case whatever we had earlier, and then in this case it would be also times 2. Don't forget the 2 for this one. It's poorly written. Sorry about that. So anyway, I have the 2. I meant to multiply cosine of x. And so then that ends up being 2 times minus 2 sine of x cosine of x, which just ends up being minus 2 times sine of 2x. So then now we get, so if you take a equals 0, you just end up getting 0. So now let's try, so then we know that for sure that the third one goes to 0. And now let's take the fourth. So we have f quadruple prime of x equals minus 4 cosine of 2x, which means that a equals 0 gets you f triple prime of a equals minus 4, which means that finally we get to have our approximation. Let's just get rid of some of this stuff. So now we have our approximation to be f, and we'll call it the fourth x, to be roughly, pretty certain this is it. But let's just confirm it's minus. Well, do we have minus 4 or do we have minus 2? Oh no, it should have been minus 4 because we did the derivative. Okay, so yeah, that's 1/6. Okay, let's move on. So now from chapter 3, I know I probably should have given this earlier. Yeah, so for example, remember what we had earlier for the curl, right? We're using the curl concept here. So it says, which field has a positive curl? So in this case, what we're doing is we want to go back to the curl concept. Remember the curl concept. So in this case, we don't know what V is. And so, but we're basically comparing this 0. We don't know. That's the big question. But essentially, we would have to try each one. So in the first case, basically remember the definition has to do with partials, right? But we can see that each vector length is, so if we go to case I, right? The vector, each one is constant. Each vector field looks like it's constant when it comes to x and y, right? Because they all have the same length at each given point. So if you take the partial, we know that it's probably, if you take partials, then it's probably going to be 0 because it's not changing at any given point. Same thing with case 2. Because in case 2, what happens is the length also looks the same. So the length, if you notice, is all going this way, right? So because they're all going in the same direction, and so it's not changing. Now, earlier I was going to say that part of my basis of what I was saying is that they're constant, but then also the direction's not changing, right? If the direction were changing, then it's possible that despite the fact that it has constant length, we would be able to figure it out, right? I mean, it would not possibly not be 0. But in this case, they all have the same length. It doesn't matter if it's angled. So we also know in this case that not only is the direction, the magnitude the same everywhere in the space of x, y, but its direction is also the same. So it's 0. Case 3, what we have is something that's a little bit different. They all look like they're the same length in some way, but more importantly, it looks to me like they're all they're changing direction. So clearly, it's not 0, right? So we know that this isn't 0, and so the vector field. I'm saying the vector field is changing direction. So we know that this is not equal to 0. Now we're going to go back to this because we don't know exactly what's going on with case 4. So case 4 is what's going on with case 4 is that it kind of looks like it's changing direction, but as you can see, it's pointing in a direction of the same direction. It's hard to explain, but let's suppose you were to get something that looks like this. If you were to take a vector field that looks like this, can we think of any examples? I would say, how about something that's like the circle, right? xi plus yj. So let's even see if this makes any sense. So if we have x equals 1 and then y equals 1, then that means that at this point that the vector should be pointing like that. And so that's kind of like what's going on here, right? It's kind of like what's going on here. Also see that, and x equals 0, we see that there is no, there's no x component. So it's going completely up, which is also confirms what's going on here. So this kind of looks like what's going on here, right? So if we try to get the curl out of this, let's just try to get it right now. So let's try to get the curl for this one. So let's just 0. Third one is, would you look at that? 0 minus 0. So it's 0 minus 0 plus 0 equals 0. So just by inspection, we know that, or just by the quick computation, we know that that's 0. So our only choice would have to be this one. So let's choose 3. You can confirm that 3 is in fact the answer, just because V in case 3 is actually the sort of the opposite of case 4, where it's yi plus xji, but almost nobody would notice this. This is for case. So you can go through it and you can confirm that in fact it's got a positive curl. In other words, this is greater than 0. So let's move on. Let's go to a stranger example, I guess you can say. This one, it says, a peach grower estimates that if he picks his crop now, he will obtain 1,000 lugs of peaches, which he can sell at $1 per lug. However, he estimates that his crop will increase by an additional 60 lugs of peaches for each week that he delays picking. But the price will drop at a rate of $0.025 per lug per week. In addition, he will experience a spoilage rate of approximately 10 lugs for each week he delays. In order to maximize his revenue, how many weeks should he wait before picking the peaches? All right, the way you approach a problem like this is you have to realize that there's probably a lot of information that's just stupid. For example, it says, in addition, he will experience a spoilage rate of approximately 10 lugs for each week. That could have not been said if it had already been factored in. In other words, obviously, it just means that you have 10 less lugs, which means you have overall 60 minus 10, which is 50. So let's just consider that this actually means if we take this crap out, then this means 50. So just to reduce the problem. So because it says 50, we know that that basically he's going to have 50 overall each week, so that if he takes 50 and then, you know, I mean, in other words, if he keeps waiting for each week, then he's going to get his money's worth for 50 times each week, times 1. He basically wants to see, okay, well, if I have 60, if I keep waiting, then I'm going to keep accumulating lugs. So if I have 1,000 lugs to begin with, then I can add that to 50 times the time in weeks. And so then that's going to be how many lugs I have. And so because of that, if you want to get your money's worth for the lugs you have, then we'll have to multiply it by however much money that you're going to have, or how much the currency is going to be per lug. So the lug here, it says he can sell at $1 per lug in the start, right? So obviously you take $1, and because each week he delays, it's going to be 0.025, right? So then that's just 0.25 times t, because it says per week, right? So then, and then the 60 portion, it says is also per week. So then that's going to be the money at time for the week. So basically it says, in order to maximize his revenue, how many weeks should he wait before picking the peaches? So this is basically the revenue. It doesn't say like what his extra costs are going to be or anything like that. So we know this is just revenue. It doesn't say that has to be profit, you know. So anyway, so if we factor this out, we basically get, well, without doing that, we want to say, we essentially want to maximize. So what does that mean, right? Well, remember earlier what we talked about was the idea of a concave down curve, right? So if the concave down portion is 0, I mean, if this is the maximum, then that means that the derivative is 0 at the maximum or minimum, depends on, you know, so and minimum. So just remember that. So we essentially want to get, and if we know that y is the money of t and t is x, then obviously we just take the derivative and set it equals 0, right? Everybody should know that. So then the money is equal to 1,000. Well, you could also just take the derivative. So let's take the derivative. We could use a product rule here. So let's use a product rule. We got 50 times 1 minus 0.025 t. And then we have plus 1,000 plus 50 t times minus 0.025, because we're using the product rule. So set that equals 0. What do you get? Well, let's just see. You get that t, we have to move everything on one side, so we get 50 minus 0.025 times 1,000 is equal to, we could say, well, in this case is t star, whatever you want to call it, t star, that 50 times 0.025 times t star, and then, because you're moving it on one side, so then plus the same thing, in this case, 10 weeks. And so then that would be the answer. So you can pause the video and see what that's all about, but let's go ahead and move on. Anyway, so now we're on the topic of differential equations and transformation. Let's move on. Okay. So it says a common class of ordinary linear differential equations is the following. You know, that's kind of pretty obvious, right? This is basically the most common class for engineers. We don't use Basel functions. We don't use any of that crap. So this is, well, in some ways, because you could do a lot of really easy manipulations with that. But let's just move on. Then you've got, you know, your overall solution to this form, which is the fact that which is the fact that you can take the homogeneous solution and add it to the particular solution. But what you have to understand is the fact that, yeah, I mean, that's just for higher powers, right? So if it's equal to 1, then you only have one type of solution, and it's really easy. I can refer you to the page number this is on. The first order doesn't use YP because both of them, because it's only for higher power. I guess page 30 kind of gives an idea of what it might be like. But anyway, let's move on. So yeah, that's what the third, first order differential equation is going to be like. You get second order, and so then for the second order case, you have the solution is of the form, and this is overdamped. The solution is of the form this, which is critically damped, and then if it's underdamped, you get some kind of imaginary solution, because it's the square root is less. The argument in the square root is less than 1, or is less than 0. So anyway, if you get a problem like this, just go ahead and just, most likely it's just going to be a form question, and just follow exactly what this is laying out for you. Anyway, let's move on. So here's an example. It says, what is the general solution to the following differential equation, right? So like I said, again, a lot of times you have the right-hand side is 0, and you just get a lot of weird stuff. So we know this is second order. So the first thing we want to note is that this is y overall solution is going to be yp plus yh. So then now we got to look up both, and well, that's the thing, because the right hand side is 0, so we only have this, and so as a result we could just use the rules. So let's go back. We see here that what we're trying to do, if it's because it's in this form, the overall solution has to do with is just going to be the homogeneous solution, which is going to be something like this. So let's consider the form. So is it, first of all, we got to ask ourselves, is it in this form? Well, the form is of the form y double prime plus y prime plus by equals 0. And so this is in the form, and such that a equals b equals 1. So then that means that we can be algebraic and say that a squared is equal to 1, which is less than 4 times b, which is 4, right? Thus, we have an underdamped solution. We have underdamped, and what you get is that y is of the form e to the a, and then it gives us what the alpha should be. So alpha is a over 2, and then we have, so our answer choices have to do with the square root of 3 over 2. Yeah, means that we can eliminate this one and this one, so we're only left with a and b. And so because we're left with a and b, let's just see. Well, alpha is minus 1/2, so clearly it would have to be a. So that's also out. So then clearly a is the answer. And so those are the type of problems you're going to... Now, oh god, so pretty comprehensive topic. It's Fourier series. But because it's, like they were saying, series are orthogonal on the interval 0 to t, it's actually a computational idea. So it's not just so super arbitrary. And that's what makes these problems, Fourier series, so mathematically draining and insane. So here's an example. So it says, what are the 3 general Fourier coefficients for the sawtooth wave shown? To do this, then let's start with a naught equals to 1 over t that have a discontinuity. But that's okay, because that's technically means that this is the period. So it's defined, the continuity, the period is defined as, in this case, as the continuity, discontinuity. So we have it as that weird, strange discontinuity. So what we have here is, this is obviously 1, so, and then at t equals 2, only define this for a given region. So, for example, for t, it'd be between 1 and 0. So, and it's different regions basically. So, you basically have this thing, and we're just using the definition, and so it's t, and then dt. So clearly, this is just t squared over 0 from 0 to 1, t squared over 2, so then that's 1/2. And so automatically we can eliminate this and this. So now we're left with b and d. Which one is it? Well, this is somewhat complicated. Let's just think about it conceptually, though. If we end up, basically, if the integral goes to 0 for an, let's just check to make sure. Hopefully it does, but let's just see if it does or not. An is equal to 2 over 1. Remember, because let's just t. Keep it not. Just remember it's 2 pi times t, I believe. So, yeah, so then it's kind of irrelevant because we're just testing to see if it's this or the other or that. So, because remember, it's either got to be 0 or it's got to be non-zero. So we don't really care about what's here. So all we're testing, that's all we're testing, because then that'll help us eliminate which answer is going to be it. So the only thing that matters is our computation of t cosine dt. And if you recall from calculus, this is going to be whatever. So if we evaluate this from 0 to 1, then what we would do is we would say, okay, well, everything kind of works out at 2 pi in the argument because of the way it's set up. So if it's 2 pi inside for sine, and we get 0, right, because we end up at 360 all over again, and 0 for here. So clearly this is 0, because we only have sines. So because this is 0, we know for sure it's b. So hopefully that made sense. We know to eliminate this. So this is just a test method, because you really have to make sure you go as fast as you possibly can on these things. I'm just trying to... Okay, we're going to start now with Chapter 5, Probability and Statistics. And so the first thing we're going to start off with is probability. Okay, so let's go ahead and start. So with probability, usually if you're going to be given a really simple problem, you're going to be using this formula. And this formula is actually, you should have seen it somewhere in your career, or your school, but essentially what it means is you're getting the OR. So, oops. In this case, we care a lot about we care a lot about what happens, what is the probability that either two events are going to occur individually. So that's why you would have to subtract out the intersection, which is most of the time the P of A and B is going to be equal to P of A. If they're independent, it's P of A times P of B. And, that's pretty obvious. But let me get this situated. And if it's independent. So what we have here is P of B. And this only holds if A and B are independent events. So basically these are the only things that you need to know, and everything else is just basic logic. So let's move on. So let me get rid of this. Okay, anyway, so next thing is sort of goes back to the same thing, but instead it's such that you have dependent events. So here it says law of compound or joint probability. If neither P of A nor P of B is zero, P of A B is equal to P of A times P of B given A, which is equal to P of B times P of A given B. And now those would have to be equal to each other if they were independent, obviously. So this is just kind of a restatement of what I just said, but in such that it's dependent. So yeah, it says it right here: the probability that B occurs given that A has occurred. So, and then if either P of A or P of B is 0, then P of A and B is 0. I mean, that's pretty obvious. And then Bayes' theorem is kind of like you're taking a fraction of all the dependent, intersections. So you see here how it's the sum, right? So if you want to find out, Bayes' theorem is basically just a way of talking about the relative probability if you look at like a sort of a tree. So if we look at a tree in a way where we start with, some event and then it extends over and over again to other events, then basically the question becomes, and then that just keeps extending, right? And this is where it starts. If you start here and then it finishes somewhere, then Bayes' theorem describes probabilities involved with a tree. So with this type of decision, they call it decision tree. So in a decision tree, what you're basically doing is you start with one event and you're saying, okay, well, what's the probability that that's going to happen? You say P of, you're going to say like P of A, P of B, and these are all like, you can see these as decisions. So P of D, I usually like to joke around by saying that you're making many decisions when you look at a bag of chips. You just keep eating one. You're making tons of decisions. You're saying, okay, I'm going to eat the chip. No, yes, no, you know. Anyway, so without further ado, this is basically what you're thinking about when you're trying to do this. Because then once you go over to one set, because when you say P of A, it means that you know that A is going to happen over here. So once you're over here, it's P of some other type of event, which we don't know. It could just be some arbitrary thing, but then it's given A. And then same with this, it's also P of whatever, which we don't know yet, given A. And then over here, it's kind of the same thing where it's P of something, which can be totally different given B. So actually, I should put that in there instead. And so this is the concept of Bayes' theorem. In fact, it works when I'm thinking about investment decisions. In fact, I mean, it's just a very sort of a logical way of handling reality. It's actually very useful on a more abstract level. You don't need to be very quantitative when you're thinking about this stuff. But let's just sort of look at the terms, right? It says P of BF, right, times P of A given BF. So that's as if the BF is almost as if it's the event. It's the event that you start that stems from the start. So A could be BI. So in other words, A could be BI, B could be B2, or sorry, B1. B could be B2, C could be B3, and then D can be B4, and so on. So you could think of it as Bayes' theorem is just a way of accounting, of getting future, of knowing what happens, of future accountability. Assuming the future will influence past decisions. So if that, hopefully I hope that makes sense, but basically what you're going to be doing is you typically in a Bayes' theorem problem, which you probably won't see on FE, I'm just making you see all this, is if you would see something, they would basically give you something from the past and then something from the future, and you're just relating the two to each other. You're basically saying, okay, what's the probability that this thing will happen? That this event A, B, C, or D is going to happen, given that we have this catastrophe way later on. So hopefully that made sense. Give you an intuition for that, and I think it does. I mean, if you think about it, right? We would want to know how the future is going to influence the present. Is basically all you're doing. So let's move on. So now we're on to the binomial distribution, and forget this because that should not have been in there. So remember, this is all probability still, and so the binomial distribution basically has to do with a very abstract way of listing probabilities, and it looks like a set, so that you're using the law of probability to determine what the overall probability is. So now that sounds like a very strange definition, but basically I'm just telling you that because all you have to do is use the damn formula. So just all you have to do is use the damn formula, or better yet, use the calculator. We could say you could use, but just stick with calculator. And then the other thing too is that I want to say is a lot of the times when you're doing probability problems, well, I'll go over that a little bit later. So next thing is now we have the normal distribution, and so the normal distribution is sort of a similar thing, but instead it's distributed instead of a discrete thing. So it's sort of a continuous problem rather than the discrete problem. And so when you're looking at a normal distribution, you're looking at basically the density of the probability over that would span over a quantity. So what that means is that if we have a normal distribution, then the probability distribution is going to be f of x, in which this might be 0 right here, and you will have something with a skew of 0, a bell curve with a skew of 0, and where this is the mean, and this could be just anything. So, but then the actual probability of x is going to be is not going to be anything. Why? Because you need a range. Oops. So, because it requires a domain, the probability really has to do with what you specify. So you could say probability of A less than X or B, and you could also say some other things. So that's going to be the integral from A to B of f of x dx. So then that's just the area under the curve. So you could say that in some reference value, so this is going to be P of some range. So that would be the normal distribution. And now let me tell you something else that's good. You're going to actually like is for FE problems. 99% of the time, for probability, only uses binomial or normal distribution. So if it's not easy to where you can use this formula, oops, then this is the easy one. Then you're going to be either using the binomial or the normal distribution. Now, that's pretty easy because you can just use the calculator. So I'll demonstrate that as we go along. But let me just cover a little bit of what each variable means. So going back to the binomial distribution, P means it's just the probability that of success, and then Q is the probability of failure. So what that just means is that if you have some particular expectation for how something should go, and you want to know the probability of that, so you might say, okay, well, what's the probability that I'm going to be able to pass the FE? Well, then you want to know. You basically want to think in an inverse way. You want to know what the probability is that you're not gonna pass. So failure is a relative concept. Success and failure is a relative concept. Success and failure simply means that one thing is true, is the probability of one thing being true is success, and then failure means it's the probability that it's false. That's all it means. And by the way, this does not, the normal and the binomial distribution do not use intersections. So just keep that in mind. It's just, if you're going to be using it to sum problems up, or sum the probabilities up, you don't need to use, in fact, you should not use the intersection. So now going to the normal distribution, we see here that this is some really fancy formula where it describes the bell curve. And, it all makes sense. This symbol mu is the x bar. Why say x bar, but it should be mu. Is x bar is pretty common. Is the mean. The sigma is the standard deviation. And then obviously sigma squared is the variance. So I'll just keep that in mind. I'll just note that we're not on statistics yet, but I'm just saying this is variance. So just to keep you going. Now, this is actually kind of important. If you're not going to use a calculator, the normal distribution problems are going to be a PITA Calc. It's a pain in the you-know-what, because what you have to do is realize that you have to transform it to normalize. In other words, to get a z-score. And the z-score is just very strange. I guess, if you haven't done the problems for very much, then you're not going to see it interpreted as easy. You're going to see it as hard. Other people, statisticians, are going to view it as easy, but you're going to view it as hard. So basically what you would do in that case is you would just calculate the z-score and then use Rx and then reference the range that you're trying to find, and then just find what the area is from that. And you'll get it. It's easy. So anyway, let's move on. I could do some of these problems. Anyway, so that's exactly what I was saying. That you would be using this table if you didn't use the calculator. So let's see what I wrote here. 99% of FE problems are either easy to the point that the leftmost formulas can be used, and by that I mean this, right? Or use binomial distributions, or use a normal distribution. And then I say, and the calculator takes care of that, and the calculator also takes care of that. So the calculator can do a lot for you, and like I said, it's going to save you a lot of time. So let's move on. I will try to use the calculator to show you exactly why it's useful. All right, let's move on. Anyway, so let's see an example. It says, measurements of the water content of soil from a burrow site are normally distributed with a mean of 14.2% and a standard deviation of 2.3%. What is the probability that a sample taken from the site will have a water content above 16% or below 12%, right? So if we're going to do a problem like this, we basically want to know what P of A and B are, right? So in our circumstance, A is going to be, technically it's the event in which X is, you could say X is less than 12%, and then the event B is X is greater than 16%. So you're basically calculating P of X you could say less than 12%, or x is greater than 16%. And by the way, remember, binomial distributions do not use intersections. You could just sum it up. I'm sorry, both of the distributions, normal and binomial. So if we're going to do a problem like this, we're going to be using the concept of normal distribution. Why? Because it says normally distributed, so we'll just go ahead and use that. So if we look at a potential plot for how this should be, then we might look at something like this, because remember, it's skewed at 0%, at 0 by 0. So, and it doesn't, even though it doesn't look like it. So this is going to be your mean, which is given as 14.2%, and then you'll have some value 12 here, and then 16 here. And so basically you're calculating the probability given by the areas that I've just outlined here. So in order to do that, there's two ways. You can take, because we know that the area under the curve for the entire curve is going to be 1, we can subtract that from the area of what's inside. So what we can do is say, okay, we know that the sum of, or I should say, the integral from minus infinity to this of any distribution is equal to 1. Thus, or therefore, we could just say P of x less than 12%, or x greater than 16%, is going to be 1 minus P of x being between 12 and 16%, right? So that would be the way you do it. However, we do not want to give ourselves a headache on the exam, right? So we're going to be using a calculator. And as you could see, I'm going to be using the calculator, and please watch out for the preceding video, and you'll see, or the next video, and you'll see what happens. Okay, thank you. So if we go to stats, and you see how it says distribution, you have basically three or four choices, but you're really only concerned about normal or the other one, binomial. And so if we go to normal, if we go to CDF, because it's cumulative, right, then we can have a range for it. If we have a range, obviously for us we want to have 12, and then in this case 16, because of the way that we wrote it out, right? So this is 16, and if we find out what our mean should be, this is normal. The mean is 14.2 if you didn't see, and the standard deviation is 2.3. So then we go ahead and give our range. I'm sorry about that. 12 and 16. We get 0.614. 0.614 is that, and as a result, we will go ahead and put that in the presentation. Okay, so you went ahead and saw that video. It said that we have, that basically this value turned out to be about 0.613. So we get 1 minus 0.613, which is about 0.38 or something like that. So clearly this is the closest answer, and yeah, I mean, that's basically the answer. So hopefully that's convincing you that the calculator works magnificently, and you didn't have to do any chart referencing or making your eyes strain from any strange disturbances. You didn't have to do anything like that at all. So hopefully that worked for you. So anyway, let's move on. So now we're moving on to a more complicated example. So this one, it says, and now it's hard to see because it's blurred, but it says, what is the approximate probability that no people in a group of 7 have the same birthday? So there's 2 ways of approaching this, and I would say the FE way is the less conventional way, but I think it works magnificently. So the typical way of doing this, the FE way of doing this, is the following. Because this is what's going to save you time. You want to be able to just say, okay, well, I don't care how clever I am. I just care about whether I can use the formulas. So what you're going to do is you're going to say, okay, well, the probability that basically no people of a group of 7 is has the same birthday is going to be equal to 1 minus the sum of the xi, you could say xi, such that I is the starts at 2 people, because there's no other way that to 7, such that this is a binomial thing, and then multiplied by 365, because this gets you the number of this gets the probability such that it's just for one birthday. So you have to do it for exactly one birthday. So you have to do it for every birthday, and once you do it for every every day, then you get the probability that it's about equal to or that you have just any birthday, right, or just any day. So because this talks about just any birthday. When you're talking about the just a particular day, then you would only use this. You would only use the binomial calculation once. So in this case, I know this is insane. So what you could say is that this is approximately 1 minus 365 times what you could say is x1 plus x2 plus ... right? And basically what you're going to say is well, this is about 0. Why? If you calculate it using your calculator, this actually is gonna, it turns out the x1 is gonna dominate. This dominates all later terms by a multiple of 100. So we know that this is just about 0. So the FE way is just to do it this way. And let's go ahead and calculate it. So this is going to be equal to 1 minus 365 times, and let me show you how to do it on the calculator. Just keep in mind. So if I start with my calculator and I go to the stat thing and then go to distribution, go to binomial, then it's going to be a PDF. So if I go to PDF and this, the binomial PDF. So if we go to binomial PDF and we have 2, right? Then we have this number, 0.0001554. So let me write that down. So what we had in the video is basically that this is going to be multiplied by 0.0001554. And so what do you get from that? Well, you get that that's equal to 0.943, and that's about the last option. So that's the answer. So basically, if you were to try to account for, again, like let me summarize, account for all the other terms ahead of time, it would just start going to 0. Go ahead and use your calculator to verify that that's in fact the case, and you'll see. So this is more of a mathematical way that you can make a shortcut, but it's also a practical one because you're using the calculator in a very easy way. So, and this is the only type of probability you're going to see. So make sure that you have this in mind so you could just go ahead and get through that exam like I did, which is just bang everything out as fast as possible, and then also make sure that you're you're poised. So anyway, let's move on. Anyway, so we have no more probability. Thank goodness we could clap now, right? And that's all you're gonna see because 90% of the time you should be able to handle it that way. If you can provide me some counter examples that you saw from your own exam, that would be great. I know that some GRE problems, probability problems, certainly don't allow you to be this general. You have to actually think a lot harder. But at any rate, let's move on. Anyways, for the statistics, it says the variance of the population is the arithmetic mean of the square deviations from the population mean. If mu is the arithmetic mean of a discrete population of size n, the population variance is defined by sigma squared equals 1 over n times x1 minus mu squared plus x2 minus mu squared plus dot 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 plus xn minus mu squared. And that is given by the sigma, right? Or the other sigma, the big sigma, the sum sigma. So then now the standard n, so that's what I mean, like this sigma. So the standard deviation formulas are, population is the square root of 1 over n times the sum of that, whatever that is, of the variances, so basically, or well, actually, the square root of the variance. But what I wanted to explain in this case is you see all this junk, right? Obviously, you can reference all these formulas, but there's a key difference between this and basically this. And now there's nothing wrong necessarily in our heads about what these things should be, but that n minus 1 is really, it makes all the difference in the world. So the fact that this is a sample makes it its own type, and this is a population also makes it its own type. So the difference between the two is basically, without making it complicated, is just that they have their own quantity. So it's not like, so it's as if they're apples and oranges, and thus you can't mix apples and oranges. So when you see that it asks you to find the sample mean or the sample standard deviation, sample variance, whatever the case might be, you have to use the sample information, or you have to use the population information only if that's what it is. Otherwise, it's a complicated transition. The transition between sample and population and vice versa is very complicated, and it takes a lot more time. So the first thing to do, the first filter for these types of problems is look for quantitative similarities in givens. And this is very important because this could save you so much time. I knew when I was taking statistics in UC Berkeley, basically, you could never just figure out the problem based on this first filter. And what you had to do was you had to calculate, you had to think really hard about the problem and basically transform the sample to a population quantity and vice versa in a very strange way. And for me, I could never get it down 100%. So I just had to stick with my guns. But for the FE, it's as simple as most of the time you're just given a bunch of redundant information, and you can actually use similar information just to figure out what it is. You don't to figure out what they want to ask you is, and it's very simple. So let's move on, and I'll provide an example of that.